Hello AP Chemistry, this is Mrs. Knotts and welcome to an instructional video on calorimetry. Before you go any further, make sure that you've printed out a video guide from the website right next to where you found this video, and also make sure you have a calculator and a pencil. For the first part of the video lesson, we're going to do a quick concept review from the hand warmer lab. At this point, you should have already completed the hand warmer experiment. And we just need to review the concept, where does the heat come from in a hand warmer? Go ahead and try this one on your own. Use the diagram here to assist you in your explanation and think about the 3 steps of the solution formation process. And you can pause me while you do that and then go ahead and when you're done answering it, just go ahead and play the video to check your answer. What you want to talk about when you answer this question is that step 1 is the expansion of the solute particles, in other words, separating them from each other. That step is always going to be endothermic. It requires energy to go in order to separate particles that are already attracted to each other. And the second thing that needs to happen in the solution formation, step 2 here, which is also endothermic, the solvent particles have to also expand and separate a little from each other, so that the 2 phases can mix. And then step 3, that's the formation of new attractive forces between the solute and solvent particles. That step is exothermic. So different salts can give different results in terms of heat being overall released or absorbed. But in the hand warmer lab, we wanted to choose a salt that would give us an overall or net release of energy. So that means that the absolute value of the heat that's associated with step 3 has to be bigger than the absolute value of the heat change that's associated with steps 1 and 2. So there's a net release of heat to the surroundings. The excess heat that results from the exothermic step is going to go into the surroundings and into the hand warmer solution and then transferred to the person's hand. Alright, the next thing that I need you to look at is the diagram. There are 2 diagrams here, and one of them is going to show you an exothermic process and the other one shows an endothermic dissolving process. So take a look at these. It's just a slightly different representation than what you saw above, and classify each one as exo or endothermic. And go ahead and pause the video while you do that, and then you can check your answer. For the first diagram, if you look at the magnitude of the arrow associated with steps 1 and 2 together for the solution formation process versus step 3, you can see that there's more energy released as this solution forms and the solute and solvent particles attract each other than what gets absorbed to separate those particles from each other at the beginning. So since the exothermic step's greater in magnitude, then the overall result for this solution formation is exothermic. For the other diagram, it's exactly the opposite. Your step 1 and 2 together, the endothermic part, that's of larger magnitude than the exothermic part here. So endo wins over exo in this case, and that diagram is showing you what an endothermic dissolve would look like. The one on the left would be good for a hand warmer, and the one on the right would be good for a first aid cold pack that uses chemicals. And then one more question for you, just to see how you're doing so far in calorimetry. We need to review why it is that chemists will classify solution formation as an ambiguous change instead of saying that it's purely physical or chemical. Pause the video, write down what you think the answer is, turn it back on to check your work. Alright, for any solution formation, you're going to produce a delta T, change in temperature. surroundings. Okay. And that's just like a chemical reaction. And that's because the delta T in either case is the result of the net bond breaking and bond forming energy changes. But again, what keeps this from being purely classified as chemical is that we're not making a new substance here in a solution formation. It's a mixture. Okay? So let's add a note there that solution formation does not result in a new substance. It's just a physical mixture. It can be separated by physical methods. Now we're going to move on to some calculations. But not only are we going to do some calculations, but we're going to transfer the ideas from calorimetry that you've already been exposed to a true chemical reaction situation. All the calculations that you did in the hand warmer lab were based on solution formation, so we're going to look at some that are chemical reactions instead. And you're going to see that there's so much similar here. It's really not a new kind of problem at all. All right, so for the first one, you've got a coffee cup calorimeter, much like the kind you used in class for the hand warmer lab, and it gives you 50 milliliters of 0.1 molar silver nitrate and 50 milliliters of 0.1 molar hydrochloric acid. And they're mixed to yield the following reaction. And that you're going to get right here is a precipitate. Okay, and it gives you the initial and final temperature of the solutions. And we need to calculate the heat accompanying the reaction in kilojoules per mole of silver chloride formed. And it gives us some information to keep in mind here. All right, so if you'll notice, you also have a diagram that I've provided with this question. And this is one for an exothermic chemical reaction. What we want to realize first is that A and B, the reactants here, are going to have to be separate. In this case, our reactants are silver ion and chloride ion. They're dissolved in the water initially in two separate containers. They have to be separated from the water molecules that are solvating them. So this step right here involves breaking the attractive forces between the ions and the water. And that's going to be endothermic. That's why you're going up the hill. That's also known as the activation energy for this chemical reaction. And then to complete the reaction, then new attractive forces are going to form between the silver ion and the chloride ion in the formation of the precipitate. So over here, we're forming attractive forces between silver ion and chloride ion, and that is your precipitate. So that should look familiar. First energy goes in, then energy comes out. And in our case, this is going to be an exothermic reaction. We can tell that from the change in temperature of the surroundings that's provided, but this diagram matches the chemical reaction. All right, so the first thing we need to do here is realize that the temperature change is that of the surroundings. All the chemicals in the coffee cup calorimeter are your surroundings. So let's get that first. All right, we're going to calculate the heat energy that the surroundings absorb by MC delta T. And if you look in the question, it's giving you permission to use the mass of all the contents as 100 grams. And this is because you've got about 100 milliliters of solution and it's mostly water. So we're just going to make that assumption. And it also gives you permission to use the specific heat of water as that of the solution. Okay, and we also have a temperature change, and you need to remember to always do final minus initial. but that comes out to a 0.8. That's a positive because the surroundings are heating up. And that answer calculates to 334.4 joules. And again, that's the heat that's absorbed by the surroundings. But this question asks, what's the heat that accompanies the reaction? So it's asking for the delta H, the change in enthalpy for our chemical reaction. That is the system. The chemical reaction itself, that's what chemists are interested in, so that's our system. And it wants the unit to be in kilojoules per mole of silver chloride formed. Okay, well the kilojoule part's going to be really easy. I will also, note, have to change the sign on my answer here because now I switched over to the system. So this should be negative 0.3344 kilojoules divided by, okay, now I've got to work on the moles of silver chloride formed. They made this pretty easy on us. Okay, let's come back up here and look at this equation a little bit more. If you see in the given quantity, you got 0.005 mole of each of your reactants. Your silver ion, 0.005 mole, same for the chloride. And that means the silver chloride precipitate is also 0.005 mole because they react in a 1-to-1 ratio. So there's no real limiting reactant here. We have a stoichiometric mixture. So I'm dividing by 0.005 mole of silver chloride. Okay, and then that answer is negative 67 kilojoules per mole. Okay, now notice that the textbook answer is off from me by 1. That's because the textbook has a tendency to round within the calculations because they show you the sig figs that they get along the way, so you can follow the sig figs. But best practice is to round at the end. But either way, it doesn't make a huge amount of difference here. So that is your answer, and that's kilojoules per mole of AgCl, silver chloride, because that's what they asked for. Okay, let's do another one. All right, here's our next problem. We've got another coffee cup calorimeter, another chemical reaction. Okay, this time it's acid-base, and we are given the original temperature and the final. And we've got some more information we can keep track of there that we need to use. And they want to know, again, what's the enthalpy change for this reaction? This is a neutralization. We had a precipitation, now we've got a neutralization for this one. So you should be fairly comfortable with those, considering all the work we did in Chapter 4. All right, and we make the assumption that no heat is lost to the surroundings, meaning outside the cup, or the calorimeter itself. So, of course, that's not a perfect assumption, but it makes doing these problems a lot easier. So for this one, looks again like, we need to specify the unit here. We're going to work this one in kilojoules per mole of HCl neutralized. Again, we've got a stoichiometric mixture. If you look at the reactants, that's going to be 0.1 mole of HCl. It's the same for the sodium hydroxide. Sometimes the problems will ask you to divide by the limiting reactant moles. In this case, it could have been either one because they're the same. All right, so let's do this one in a similar fashion to the other one. We're first going to start with the heat energy that the surroundings absorb because that's what the temperature change is showing us. Okay, and this one's going to be 200 grams. We can assume the density. It tells us to assume the density is 1. So if we've got 200 milliliters, we've got 200 grams. And then our specific heat is going to be assumed to be close enough to water to just use water. And then the change in temp is 6.7. And again, it was a positive because the surroundings are heating up. And that means we're going to have another exothermic chemical reaction. That one calculates out to 5601.2 joules. So that's the heat absorbed by the surroundings. But we need the change in enthalpy, the heat change for the reaction, and the units have to be kilojoules per mole of HCl reacted. So that is going to be negative 5.6012 kilojoules divided by 0.1 mole HCl. Okay, and that just comes out to negative 56 kilojoules per mole of HCl reacted. That's not surprising for an acid-base reaction. Those are always exothermic. All right, we've got one more, and this one's a little more complicated because it's another acid-base, but they weren't kind enough to make it stoichiometric mixture. Okay, we've got a limiting reactant here. I prefer to work all of these with the net ionic equation because it forces me to look at how much hydroxide and hydrogen ion I truly have, so I don't make the mistake of ignoring something like barium hydroxide, which a lot of students will do. They won't think about the fact that there's 2 hydroxide ions in each formula unit there. All right, now if you look at the given information here, you can see that the moles of the hydrogen ion come straight from the hydrochloric acid, and that's going to be 0.05. Just multiplying molarity times liters like we always do. Now the hydroxide, first you can get the moles of the barium hydroxide, that'll be 0.03. But if I want hydroxide ion, I'm going to have to double that because each mole of barium hydroxide gives me 2 moles of hydroxide. So this is actually 0.06. If you don't pay attention to that, you could easily get your limiting reactant wrong. That, the hydrogen ion, is the limiting reactant. All right, so with this problem, it's a little bit different. We're not solving for the heat of reaction. We've got it provided for us. It's right here in the problem. As written, that's what it is, based on the reaction as it is there. They want us to find out what the final temperature of the mixture is, given the information provided. So we're going to have to work this one a little bit backwards. I know that I'm going to react 0.05 mole of hydrogen ion because it's the limiting reactant. So I'm going to use that plus the information from the thermochemical equation to figure out how much heat energy I'm dealing with here. So this is the amount of HCl that's getting reacted, but if I look at my chemical equation, I can see here that for every 2 moles of HCl that I react, I'm going to get out 118 kilojoules of energy, exothermic. So that comes out to 2.95 kilojoules released, exothermic, and that's the same thing as negative 2950 joules. That's my Q, okay? That's my heat for my system, okay? That's Q for the system. But when I do my little calorimetry calculation with MC delta T, I'm going to focus on the surroundings because that's what the temperature change corresponds to. So now I'm going to be finally ready to do my MC delta T, but it's going to be for the surroundings. Okay, so I have to, guess what, change that sign. Okay, now it's positive 2950 joules. Okay, and that's going to give me mass, that's 400 grams. You can get that out of the problem. The specific heat, we've got that assumption again, we're going with water here. And then the delta T, well, we don't know that because we don't know the final temp. I like to set it up like that and just solve for the delta T and then find the final temp. Since I know the initial, I can work with that at the end. It makes the algebra somewhat simpler. So if you solve this for delta T, then you're going to get 1.8 degrees Celsius. And of course, that's an increase. The surroundings are going to warm up. This was an exothermic reaction. The system experienced an exothermic change, so the surroundings experience an endothermic change. So the temperature of the surroundings goes up. If I know that my initial temperature was 25.0, then my final temperature is going to be 25.0 plus 1.8 Celsius. Okay, and that's going to give me 26.8 degrees Celsius for the final answer. Okay, well, I hope that these examples helped you to see how to work calorimetry problems. These are all constant pressure calorimetry problems or coffee cup calorimeter problems. That's the kind that you will need to know for the AP exam. Thanks very much for tuning in and taking the time to watch this and learn more chemistry. And let me know if you have any questions about the video. You'll find a short quiz for multiple choice questions next to this video guide on the website. You can try that out, take it, and you can check with me or Mrs. Hamilton for the answers in class. Thanks very much. Bye-bye.